Hey there, everyone. In today's video, we'll be talking about how to create a player controller both in 2D and in 3D. So first here, we have our 2D project in Unity 2022. The first thing we have to do, we have to create both the ground object and the player object. I have here, since this is 2D, we'll be going to 2D objects, sprites, and opening up the square one, just to make a simple square for the ground. Let's scale this up. Center it out. There. And we can bring this down. Also, you can change the color of the ground from here in the sprite render of the object. Next, so here we have our player object. I used the prefab to make it quicker. So here we have a simple player who we call Buck. He's just a square with two eyes. Now, first things first, we need everything to have colliders. Since Buck will be using the ground, we'll have to have a box collider. So let's go to add component and add on a box collider 2D. Remember, this is 2D because we're in a 2D project. You can see automatically there's already collider around Buck. See? Next, we also have to add one for the ground here. Box collider 2D. And there we go. Let's step one out of the way. Next, we need to make sure that when the game plays, Buck will be falling to the ground. Of course, we have to simulate physics, so we'll be needing a rigid body component. Now remember, 2D again, so we'll be choosing rigid body 2D. Yeah. Okay. Now, if we press play, you see that Buck will be falling straight to the ground, and he won't be going through it. If we remove the box collider from the ground, Buck will simply pass through it as if it didn't exist. So it's very important that we have colliders on every object that will be interacted with. Next, we need to figure out a way for us to control Buck here. So what we're going to do, we're going to create a new script called player controller, Buck controller. Here we go. Now let's open this up in Visual Studio. So here we have our player controller script open. Now we can start coding the controller. So first we're going to call public rigid body 2D RB. This one will be reference to the player controller's rigid body component. Next, we have public float speed. Now, I'm going to put a default here of 3F. And what this simply does is it controls the movement speed of Buck. And finally, we have private float horizontal. I'll be explaining in a bit what this does, or let's call it horizontal input. So first, we need to make sure that this script uh, gets a rigid body component. So what we'll be doing is we're going to call void awake RB equals get component rigid body. The awake function is called before the game starts. So essentially, even before start is called, awake is going to be called. Okay. Next, here in update, what we're going to do here is we're going to get the player input. And here in fixed update, we'll be applying the input to movement. Now, why do we have to separate the input and the application? Because update depends on the player's hardware. It's better to put it in fixed update where the updates are called on a fixed amount of time, meaning that no player will be faster than any other players. The experience will be the same across all devices. So now we're going to start making the functions for getting the input and applying that movement. So what we're going to do is private void get input. in private void player movement. Now, there you go. So these two functions will be used in the update and the fix update. So here in get input, what's important here is that we need to get the horizontal axis of the player. Now we have two axes, the horizontal and the vertical. Horizontal represented by X and vertical represented by Y. In order to have buck moving left and right, we need to get its horizontal axis here, the X. So here in get input, what we're simply going to do is we're going to call this horizontal input variable, horizontal input, and give it the value of input dot get axis horizontal. There. This get axis function simply gets the value of whenever a player presses the A or D keys, or it could also get the left arrow and right arrow keys. What this function simply returns is a value of either -1 or 1. Now, going back to the example of the x-axis, if we were to press the A key, it would return the value of -1, which will go here into horizontal input. If we were to press the D key, if we were to press the D key and we want it to go right, what it's going to do is it's going to return this value 1. Now that that's done, let's call it here in update get input. And now we have here player movement. Now that we have the value of the horizontal input, we need to apply that to the rigid body. So what we're going to do, we're going to call RB, the velocity, to change its speed equals to a new vector 2, because we're on a 2D game currently. Horizontal input times speed. And we're going to preserve whatever velocity it had in y. Why is that? So the reason why we call RB velocity.y instead of 0 is that, let's say Buck is in the middle of the air. Now, if we were to press the A and D keys, we want him to move left and right while still falling. If we change this to 0, the moment the player presses the A or D keys, Buck will just simply stop here in the middle of the air and just go left and right. So in order to prevent that, we won't be setting y to 0, but instead calling it to get its current velocity on the y-axis. And let's put this in player movement. There. Now that we have all of this, we can go back to Unity and check if the script will work. No, I don't have to reference this because in the script, it would simply just get whatever rigid body is in this game object. So let's play. And we see here, Buck falls down, and we can go left and right. See? When I press the A key, he goes left, and when I press the D key, he goes right. Same with the arrow keys. All right. Now that we have Buck moving, of course, we want this sprite here to flip around. We want Buck to be facing wherever he's currently going. So let's stop the play and let's go back to Visual Studio here. So here in update, we need a function to flip the game object based on the horizontal input. Now, let's try again making another function here called flip. Okay. So let's do a bit of critical thinking. So let's say this is Buck here again. When Buck moves to the right, we want him to be facing right. If you remember earlier when I was talking about horizontal input, the horizontal input here would be 1. And currently, if we go back to Unity, you can see here that his scale on X is +1, which is right now him facing on the right. But when he's moving left, his horizontal input will turn into -1. So we want his scale to also flip to -1. There. This is scale, and this is horizontal. So what we have to do right now is that we need to make a function that checks the horizontal input and checks the current scale. If the horizontal input is positive and the scale is negative, we want it to change to positive. And same for vice versa. So to do that, here in the flip function, we'll be doing a conditional statement. So if horizontal input is greater than 0, which means it would be positive here, and transform, which gets the current game object's transform component, which you can see here, this one. Yeah. So we have transform dot local scale dot x is less than 0, or the opposite, which is horizontal input is less than 0, in this case, less than 0, and transform that local scale dot x is greater than 0. So if these values are mismatched, what we want to do is we want to set the game object's transform that local scale equals new vector 3 transform that local scale dot x times -1 transform that local scale dot y and transform that local scale dot z. Essentially what this does is it just applies times -1 to flip around its current scale. So let's call that here in update flip. Let's move this down for cleanliness sake. There. Now let's save that and test it out. By the way, we're using vector 3 here in local scale because local scale operates on a vector 3 here. As you can see, it uses the x, y, and z value. So we need to use vector 3 as well. Okay, let's test it out here. There. So I press D, he'll be continuing to look on the right. But when I press A, boom, he suddenly turns over to the left. And if I press D, yun, he flips over. There. Now we have his simple left and right movement, as well as a visual indication of where he's headed. There we go. Now, let's add a jump feature to Buck. So let's go back to the scripts. So now that we need to code the jump feature, we need something to check if Buck is on the ground. Why so? We don't want Buck to be jumping in the middle of the air. We only want him to jump when he's on the ground. So now that we're going to code in the jump feature of Buck over here, what we're going to do is we need the code to check whenever Buck here is on the ground, and we need to add that force upwards so that he will be able to jump. So let's go over to the code here. To create the ground check function, we're simply going to create a new field here, ground check. Now this header here isn't required, but I highly recommend you create one for the sake of cleanliness and order. So here we're going to call public layer mask ground layer public transform distance object, and public pool is grounded. Now, what this ground layer does, we're going to reference this to the ground layer or whatever objects that should be considered ground. Here in distance object, this will be referenced to an object under buck. So we can say the distance where buck should be considered is considered grounded. Oops, grounded. And this one simply holds the true or false of whether or not Buck is on the ground. Okay, let's go over here and we have uh, this ground check method, and we're going to simply do this. So first, we need to create a raycast hit 2D. Now, what a hit is essentially it's essentially a boolean, but for physics raycast, but it's more complex than that. But for now, we'll be using it as a true or false. So here we have physics.raycast. For the first field, we'll be calling transform.position, which is box current position, vector2.down, which is the downwards direction from buck. What vector2 that down is, it's essentially a shorthand version of 0, comma, -1, which is from buck, you can create the line downward, and this line is valued -1. So yeah, this is essentially the shorthand version of it. Next, after this, we'll be calling the distance between our game object and the ground. So what we're going to use is this distance object over here. We still need to get its actual distance. So what we're going to do, we're going to create a new float over here. Float distance to ground and equals vector2 dot distance, transform that position, comma, distance object dot position. Yeah. What this simply does, it returns the float value of the distance between box current position and the distance object's position. So we're going to call that here distance to ground. And we have here our last field layer mask. So we're going to call ground layer. There. Apologies, this should be physics 2D. Okay, there we go. So physics 2D dot raycast transform dot position vector2 down, distance to ground, and ground layer. So after checking that, we're going to call if it, meaning if the ground is within the distance between buck and the distance object. Yeah. If it hits the ground, we're going to return is grounded equals true. And if not, we're going to return is grounded equals false. There. Now that we have this code here, we're simply going to call it here also in the update. We're going to call it before get input. So we're going to call it ground check there. And let's open it up again in Unity and see if this works. Now let's play and let's check here in the inspector. There, you see, if this object over here is the distance object, and we reference it here on the distance object area. So what it essentially does, it creates a line between here, this pivot point, and the distance object down here. And whenever this ground is within this line, the hit is going to be true. Now, I'll show you what it looks like if I bring Buck away from the ground. So if I were to lift Buck up, you see down there in the Buck controller script, it says there is grounded and the check mark goes away. If I let go of Buck, it goes back to true. So you see here, our code is working perfectly. And we can now tell whether or not Buck is on the ground. Now that we have our ground check, what we can do now is add in the jump function. So let's go back to our script. So here in get input, we want to check whether or not the player presses jump, but we also need to tell if Buck is on the ground. So what we're going to do here is a conditional if is grounded and input dot get button down jump. Now, why do we use get button down instead of get key down? Get button down essentially uses a default uh it essentially uses the default buttons for the assigned function. Like for jump, it would be like space bar. You can also toggle that somewhere here in the project settings. You can see here in the input manager, you can see all of the different buttons that you can press, the axes, and see horizontal, left, right, AD, see. So there's vertical, down, up, this W, and the jump here. And it uses just click button 3 or the space button somewhere here. That's our input manager, and that's what we're using for the get buttons and the axes. So here we have get button down jump, and we're gonna call a new function called jump. Let's create that down here. Private void jump. Okay. So what we want it to do is we want the script to add a force. Yeah, let's visualize it. So what we want it to do from the ground, we want our script to add a force upwards for Buck to jump up. Basically, essentially, it just pushes Buck up, simulating a jump. And after the jump, once it reaches its peak, we want rigid body to take back over and bring it back down to the ground so that Buck comes back grounded. Now this is simple. This is simpler now because we have a rigid body, but without using rigid body, it's going to be a lot harder to simulate gravity all over again. The simplest thing to do here is we're going to do RB dot add force, which essentially just adds a pushing force in whatever direction we indicate. We're going to call vector 2 dot up times, and let's create a new variable here called public float jump force. What this essentially does is it controls how high Buck will be jumping. Controls the jump height of Buck. There. So Buck here times jump force. And its second field we're going to call force mode dot impulse. Now, what's this force mode all about? What force mode does it indicates what type of force we want to add. If impulse around here, if we set it to impulse, on the very first frame it's going to suddenly add this pushing upward motion. So only first frame. But once it gets to the second frame, the pushing force will be gone. And what will be left is rigid body doing the work. So yeah, it will essentially just keep going up, slowly being pulled down by gravity. Once it reaches up here, it's gonna be pulled down all the way back down to the ground. Comparing that with force mode dot force, it says here, add a force to the rigid body using its mass. Basically what it does, it adds a continuous force going up. And it just keeps going up after that first frame. If you're not sure what each function does, actually here, force mode dot 2D, you can simply just hover over it using the IntelliSense of Visual Studio. Here, adds instant force, and this one force, it just slowly adds on. So here, impulse. There. There. And we have it working now here. Once Buck is grounded and once the player presses the jump button, Buck is gonna jump upwards. All right. Now let's save that and check if it works now in Unity. Now that Buck is grounded, if I were to press jump, whoop, you see that he jumps really high. Let's lower that and let's move it to 5. Whoop. See? Now he does a more soft jump. Whoop. Split 7 to get the middle ground. There we go. There. Now we have the jumping feature. Now, as you see, we can press A and B while we jump, which is a really good thing here in 2D. Now, what add force does, it doesn't completely overwrite the velocity like here in player movement. It doesn't completely change what the velocity of its x and y axis does. Essentially what it does is add force just adds that on. So whatever you have here in add force is going to add. So let's say this is 1 and this is 0. It's going to retain, essentially it brings down x plus 1, whatever force you added here, and it will just retain whatever already existed before. I almost forgot here in player controller. We also need a way for the camera to follow Buck whenever he's moving around. As you can see right now, Buck's just freely moving and the camera just stays in one place. If we were to move Buck off screen, we won't be able to see Buck anymore, see? So in order to do that, we're going to simply use the Cinemachine package. Ayan. As you know, to install this, you go to Unity Registry, search Cinemachine, and simply install it once it appears here. It's already installed here in this project, so I won't have to do that process again. So we're going to what we're going to do here is right click here in hierarchy and create a Cinemachine 2D camera. There we go. Once we create that, it automatically gives the Cinemachine brain to the main camera, sorry. And what we're going to do, we're going to assign player here to follow and look at. What this essentially does is that the camera is assigned to follow Buck wherever he goes. So if I this the play here, you see the camera now follows wherever Buck goes. Yeah, wherever he goes, he just whoop, the camera just follows along. Now you can see here we have a lot of different options for the body movement, for the aim movement. So whichever you want to do, you can just try out whatever setting you like most here. So that's about it for our 2D game project. Next, let's move on to our 3D game project to discuss how we're supposed to make a player controller over there. So now let's move on to our 3D game project. So here we'll create a new project. Let's move it back to 2022 and open a project in Universal 3D. What this essentially does it immediately loads it on the URP template and on the 3D scale. So here behind us we already have one prepared. And as you can see, I already prepared this 3D plane object, which will be considered as the ground. And here we have little Buck now in 3D form. Yeah, you can see where he's looking at now. All right. So first things first, let's go set up the player controller. So here, there are actually two ways you can do this, but what I recommend the most would be using the rigid body because it's a lot easier to simulate gravity and allows you to do collisions uh, and jumping a lot better. So here, let's go create a new script called Buck controller again. Controller. So now that we have this script open, let's start off declaring a few things first. So first, we're going to create a public transform orientation. Now, what this orientation is essentially it's going to be a separate game object that holds the forward direction of the player. This is going to be important later on. So next, we also want to do header ground check. Similar as in 2D, we also want to check the ground. So we're going to call public layer mask ground layer. And here, instead of using a game object to tell the distance, what we're going to do is we're going to create a float which holds a player height. Now this makes it easier because we can just simply assign how tall the player is and how far the ground will be from his height. It will be important later on, so I'll explain it more in detail. And of course, we shouldn't forget we also need public bool is grounded there. And as before, we need to check the horizontal input. But compared to earlier, now that we're in 3D, we also need the vertical input, which is going to be the W and A keys. So let's add that here for comment's sake. This will be the A and B keys. And this will be the W and S keys. Also, don't forget private. We should also call our rigid body. This time in 3D, so just rigid body RB. Okay. And just like before, we're gonna call awake so that we can get our rigid body component from our game object. And like before, we'll be getting our player input from and applying that. So we're going to do private void get input and private void player move. Yeah, yeah. So in get input, now that we have two inputs that we need to pay attention to, we're going to call horizontal input equals input dot get axis horizontal, of course, and vertical input was input dot get axis vertical. There we go. Now, in order to hold these two inputs into one variable, we're going to create vector3 move direction. So what we're going to do here is we're going to call move direction equals orientation dot forward times vertical input, of course, the W and S keys, plus orientation dot right times horizontal input. Now, why do we use specifically forward and right? So what this does is, let's say we have here our 3D game object. Now, we want, ayan, now we have this forward motion. As you know, in 3D, we have X, sorry, no, this is X, our horizontal, our Y, our vertical, and Z, our forward and back. Now, what orientation that forward does, it gets this value, which is whatever direction our player is currently facing. So let's say this is the Z-axis and this is its forward. It's going to get that and multiply it with our vertical input. If you remember earlier, when you press the A and D keys, it's going to return -1 and +1 for horizontal input. Similarly, in vertical input, what it does is when you press the W, it's gonna return +1, and when you press S, it's gonna return -1. So essentially, what it does, it gets whatever value you have here. Let's say you press S, and you multiply it to forward. What it's gonna do? It's gonna just go backward. And the same concept works for orientation dot right. But and I think you would also be wondering, why are we directly adding these values into a vector3 when we know that vector3 is like X, Y, and Z? Now, what we did here is we essentially got the transform, which also returns a 0, comma, a vector3 value here. Same for these two. It's essentially just the shorthand version of like 0, comma, 0, comma, 1. This is forward, and orientation dot right is like 0. Oh, sorry. It's like 1, comma, 0, comma, 0. Yeah, it's essentially the shorthand version of the vector of the earlier vector2 dot forward, vector2 dot back, vector2 up, vector2 down, and so on and so forth. Let's clear all that. Okay, now we have our input. And now we can call it here in update get input. Next, we want to apply that movement to our player. So what we're going to simply do is we're going to do RB, then add force, move direction times speed, which is our current speed, and we're going to multiply it by 10. Now, why are we multiplying it by 10? In 3D, for some reason, the values of speed and move direction are a lot lower. So just to speed things up, we're going to directly add 10 to it to make it faster. Also, don't forget, we're also going to add the force mode since this is add force and we want movement to be continual. What we're going to do is we're going to do force dot force there. And let's call that here in fix update player movement. Save that. Okay, let's start off by creating a rigid body component here on our player object. This player object over here, by the way, is an empty object holding these 3D objects. You can see here, if I turn it off, it's just 3D. It's just an empty player. It's an empty object uh, holding everything within it. And let's just add in our buck controller over here. Let's just re-import this. By the way, if ever you come across the same problem where Unity doesn't load up the script in the inspector, all you have to do is re-import that script. And now it should be good. See? Now this orientation object, we're going to add in another empty object down here under player. Call this orientation. And we're gonna reference that up here in buck controller. Assign ground layer. Boop. On that note, let's also add in now the ground checking function, private void ground check. Now, what's different here is that instead of using a game object to tell the distance between our player and the ground, we're going to directly get our player's height. We're going to get this height. Let's say this is the value of 1. Now, we're going to get the player's height divided by half. So it becomes like here, 0.5. And we're going to add, yeah, from the center, we want it here, 0.5. And then we're going to add the bit more here. So it becomes like plus 0.2, 0.2f. So we want this to create a line from here, the center of our player, all the way down down below the player. And like before, we're still going to be using our physics raycast. So what we're gonna do is here we're gonna call is grounded equals physics dot raycast. Again, transform that position to get our current position. Our direction will be vector3 dot down. And then our distance, again, from my explanation earlier, we need to create a calculation that creates the distance of half the height added to 2. So what we're gonna do is float distance to ground, player height times 0.5, which is essentially divided by 2, plus 0.2f. There we go. And let's add that here, distance to ground, and of course our ground layer. After that, let's also add in now our jump void jump. And what we want it to do, of course, same as earlier, we want it to jump whenever the player is on the ground. So like earlier, we're going to do rigid body dot add force transform dot up to get the upwards direction of our player. Transform dot up times jump force. And again, force mode dot impulse because we want it to apply once only. And now let's call that here So in update, we want it to check if the player's on the ground. Also, we want jump to be called whenever the player presses the jump button. So we're going to add here and get input in if is grounded and input dot get button down jump. And what's gonna do? It's just gonna jump. There we go. So let's go back to Unity. Let's check if our movement works. Let's load that up. Okay. Again, we have to remember this plane. We have to assign it to ground so that our player will consider that ground. We're going to assign here in player height to 1. There we go. And let's press play and see what happens. There we go. And now you can see once Buck is there, it's going to be considered that it's grounded. And if you press jump, boop, Buck's just going to jump in place. There we go. Now remember, we need our rigid body to be freeze rotation on X and Z. Why? Uh, I'm gonna remove these two and I'll show you the result. Now, if I were to remove this freeze rotation on X and Z, if I were to press A, Buck's just gonna turn over on whatever his right feels like. And there, you can see he's gonna start floating upwards when I press D because he's on his left side. And back is just gonna start doing the same thing. Yeah. So freeze rotation is really important here because we don't want Buck to be like rolling around. What we want Buck to do is that he moves around like a regular player. So we're gonna freeze those two rotations so that he's gonna move around like a tiny little box that doesn't spin. So if you notice our movement right now, when I'm gonna show you when I hold D and let go, hold D, let go, you see he slides off as if he doesn't have any friction at all on the ground. It's like he's sliding on ice. So what we're gonna do is that we're going to add new functions here that will control Buck's speed so that he doesn't keep sliding and so that it feels like he's going across an actual ground. Woo! Okay, let's go back to Visual Studio and we're gonna add a few more variables. First, public float drag. What drag does is essentially it simulates friction between two objects. So whenever Buck is on the ground, we want our drag to apply to Buck so that feels like Buck is actually moving across uh soil, not ice. So first, yeah. So remember we also have a jump function. We only want this drag to be applied whenever Buck is on the ground. So what we need to do here in update, we're going to do a conditional if is grounded. If the player is grounded, we want the rigid body's drag to be equal our assigned drag. But if the Buck is in the air, we want the rigid body's drag to be equal to 0. Uh, that way Buck will be able to move around freely in the air. Also, there's another thing we need to add here on bubbly float air multiplier. And what this value essentially does, it's a value that we're going to multiply here in our speed when Buck's in air so that the player will not be able to move as quickly in the air as they would on ground. But this could be adjustable later on. So we're gonna call if is grounded. We want we want Buck's movement to stay normal. But if he is not, what we're going to do, we're going to copy the one above, add force, move direction, times speed, times 10F, and we're gonna multiply our air multiplier to it. And same force mode dot force. That way it will be a bit more difficult for players to move back while he's in the air. Go back to Unity and let's check it now. All right, let's go check it now. Let's play. Let's see if the drag works. Right, you can see now he has a bit more hard time to move across. And now Buck has a bit more harder time to move across the ground while the drag is active. And when we jump, that drag's gonna go to 0 and our air multiplier is gonna take place. Oh, he's still really fast. But there are some instances that Buck still goes out of control. Oops. Yeah, there are still instances that Buck still goes out of control. So what we're gonna do, we're gonna add in another function called speed control to truly limit the speed, because sometimes the speed's gonna go way past 3 here. As you saw earlier when he was in air, he was so fast. So what we're gonna do, we're gonna add a speed limiter. So let's add in here private void speed control. Now what this speed control here does is it's going to get first, it's going to get current actual speed of the rigid body. And what it's going to do is if the actual speed goes past the movement speed, we're going to limit it back down to movement speed, to our set move speed. So first, let's get the actual current speed. We're going to do this by calling vector3 and creating a variable here called flat velocity. And we're going to do a new vector3 rigid body dot velocity dot x 0f and rigid body dot velocity dot z. Now, why did I exclude y over here? We want speed control to only affect the x and z, the forward and back, and the left and right movement of Buck. We don't want it to limit the effects of gravity or the jump force. So now that we have our flat velocity, we're going to check if that flat velocity goes past our movement speed. So we're going to do flat velocity dot magnitude greater than speed. Now what dot magnitude returns there? It returns the length of the vector. So whether it's positive or negative, it just returns that. It returns the actual velocity. And if it goes past the speed limit, you want it to limit back down. So what we're going to do here is we're going to do vector3. We're going to create a new vector3 here called limited vel. And we're going to assign it to flat velocity dot normalized times speed. What does that normalize do? Now let's say our speed right now is like 4 comma 0 comma -5, for example. What normalize does, it gets these big numbers and sets them back to 1. Now why do we need to do this? What we want here is we need to get the direction of where the player is currently moving, and we want to apply that to our speed so that we can regulate it back again. So what this does after normalization goes back to 1 comma 0 comma -1, and when we multiply that to our speed, which is 3, it's going to return 3 comma 0 comma -3. That way, the player will keep moving in the same direction, in the same original direction, but with our new limited speed. So what we're going to do here is we're going to add it to rigid body velocity equals to new vector3 limited velocity dot x comma rigid body dot velocity dot y, because we don't want to affect the vertical velocity, and then limited velocity dot z there. And now we're gonna call that speed control here after get input speed control there. And now we should have all those in place. So if we go back to Unity and play that now, we should see that now our velocity should be normalized all the way. No more really fast movements. Yeah, no more flying around too much there. Now it's true velocity is stuck at 3. Okay, there we go. And like earlier, we want our camera to follow Buck around. So what we're gonna do, like earlier, we need to import Cinemachine back here in Package Manager, Unity Registry, Cinemachine, and install it. And it's already installed here, so I don't need to do it. Right click down here in the hierarchy, create a Cinemachine free look camera. This should allow us to simulate a third person view camera. So like earlier, we're gonna assign player over here at follow and look at there. Now, in setting up a third person camera, there are a few things that we need to move. So of course, here the FOV, we need to bump it up a bit. And here in the Y and X axis, we need to switch their inverts. They're originally placed opposite of where you're going. Like if you were to move your mouse left, it would go right, and so on and so forth. So you want to change the inverts of both. And here we can manually adjust what each rig would look like. Now these 3 rigs here is the different peaks you can reach. So we have the bottom rig, which is represented here in this red circle, which is the lowest point we can get to. Middle rig, which is the middle point, and the top rig, which is the highest one. I'm gonna adjust this. There's no set way of doing this, but there is one that I really like using. So let's adjust it here. We want to go middle rig. Set this to 2. Radius of like 4. 1.5. No, 2. And we want this top rig to be around 3. So you can see it's 3, 4. Yeah, 4. Want it to be radius of 1.5. No, let's do 2. There, you can see here. You can see those curves over there. That's our rig now. If we play it, you see here with our mouse movement, the camera's just gonna adjust along. We press forward, box gonna move forward, back, left, and right. However, even with this 3D camera, if we were to look directly at Buck and press forward, he's gonna move forward in the actual word space. He's not gonna turn. Same with the left and right. He's not actually turning. He's just looking at the same direction. So what we're gonna do, we need a code that turns Buck around once you press W, but also we have to base it off of the camera's position. So how do we do that? In order to rotate our player object, we're going to create a new script here that will be referenced to our camera. We're going to call this relook camera, just to simplify it. And let's open it up. So we're gonna need a few things here. First, we need our public transform player, which is going to be referenced to the player parent object. We're also going to create public transform player object. This here is going to be reference to the actual mesh of the player, which is going to be the cube. And we're also going to reference it to public transform orientation. That one empty object that we made earlier. Yeah, this is where we're going to use it, orientation. Now that we have that in place, are also going to need a public float rotation speed. Sorry, rotation speed. Now what rotation speed here is going to do is going to dictate how fast the player object is going to rotate. Okay, we're not really going to use this start, so we can get rid of it. So here in update, we're going to declare a new vector tree called vector tree view direction. So what this view direction is going to do, it's going to go take our camera's okay, let's show it out. So we have Buck here, and let's say our camera is over here. So what it's going to do, our view direction here, we need to tell which direction the camera is facing and apply that to our buck over here. So whichever the forward of our camera is, that's gonna be the forward of our buck. That's whatever gonna change in orientation over here. What we're going to do here is going to call player dot transform dot position. Sorry, it's already transformed. Player dot position dot x minus new vector 3 transform that position with which gets the camera's position, transform that position dot x comma player position dot y and transform position dot z. And my mistake, this should not be dot x, should be just player position. Okay, here we have now our view direction. So essentially it gets the player position and subtracts it from our camera position, the player's current y, because we don't want to count the vertical distance of our camera and the player, and the z. Okay, now we have our view direction. And what we want to do with that is we're going to do orientation dot forward equals view direction dot normalize. Essentially what this does is it turns the orientation, that empty object we have in the middle of our player. What it's gonna do here, it's going to get this orientation object and it's gonna turn this blue axis over here to whatever direction the camera's forward is to the player. So let's say the camera is in this position, right? And our orientation dot forward is currently like that. What it's going to do, it's gonna turn that like this so that the forward direction is always in the direction that the camera is facing. After turning that, we want to get uh, the input again. So we're gonna call float horizontal input equals input dot get axis horizontal float vertical input equals input dot get axis vertical. And after getting those, we want to get the direction of where our input is going. So we're gonna go input direction equals orientation dot forward times horizontal times vertical input plus orientation dot right times horizontal input. And after that, if we're going to check if there is an input direction, so we're going to input direction is not equal to vector 3 dot 0, which is 0 comma 0 comma 0. And if it is not 0, which means there is an input. So if input direction is not equals to 0, we wanted to do player dot forward is equals to vector 3 dot slurp. And what we're going to put here is the player's object, the actual object dot forward, comma input direction. And we're gonna multiply it by rotation speed times time dot delta time so that it smoothly turns to the direction. All right, now that's done. Let's save it and let's test it out in our game project. Now we're going to go to our main camera and add in our free look camera script here and just a bit of referencing the player object, the orientation, and there's that speed. Let's save it. And now we can check once we play. There we go. Now you can see, let's look directly at Buck. And if I were to press W, there, now he turns over. If I were to look on his side and press W, he turns. If I were to look this way and press A, turn to the left and to the right and to the back. There we go. And if I were to keep pressing W, you can see that Buck over here slowly turns over to whatever direction I'm looking towards and makes it pitch forward. There. See? No matter which way I look, he's gonna move forward. I jump. Just looking at him. Whoop, whoop. There we go. And that's about it for our player controller of 3D. And that should be the end of our video for today. If you have any questions, you can probably PM me or leave it in the comments. I probably won't see it, but bring attention to it whenever. Yeah, that's about it.